All right, let's talk about a single research paper. One paper from 2017 that basically became the blueprint for the entire AI revolution we're all living through right now. I'm not exaggerating. This one paper, Attention is All You Need, completely changed the game.
And it all starts with this one sentence, right from the abstract. They say they're proposing a new architecture based solely on attention mechanisms, dispensing with recurrence entirely. I mean, that's not just a proposal, that's them throwing down the gauntlet. They were basically saying, you know that main way you've all been doing this? We're throwing it out.
So to really get why this was so huge, we're going to break it down. We'll look at the problem they were up against, the wild idea they came up with, how it actually works, the mind-blowing results, and, well, the world it created. All right, let's jump in. Okay, first things first. This paper came out of a team at Google, and you have to understand, this wasn't just a small step forward. No, this was a total rethink, a fundamental shift. It was the spark, the foundational building block that made things like ChatGPT even possible.
So to appreciate the new, you gotta understand the old way of doing things, right? Before this paper, the top models for language were these things called recurrent neural networks, or RNNs for short. And they were okay, but they had this one huge built-in problem that was basically a roadblock for the entire field. So RNNs have to process language one word at a time, in order. Imagine trying to read a whole book through a tiny straw, word by word. Not only is that painfully slow, but by the time you get to chapter 10, are you going to remember that super important detail from chapter 1? Probably not. That was the problem. They had a terrible memory for long-term context.
And that's the fundamental constraint right there. On one side, you have the old way, the RNNs, stuck going word by word, which makes them slow and bad with long sentences. On the other side, you have the transformer, which just looks at everything all at once. This sequential process, this bottleneck, it was a wall, a serious wall that was holding back progress.
So the authors of this paper came along and asked a really bold question. They said, you know this whole one word at a time thing? What if we just stop doing that? Instead of trying to make the sequential process a little bit better, they decided to just throw it out entirely. A totally radical idea. And their radical new idea was built around this beautiful concept called self-attention. This is it. This is the secret sauce. It's a mechanism that lets the model look at the entire sentence at once and figure out how every single word relates to every other word, no matter how far apart they are. So instead of that single file line of words, the model suddenly saw a complex web of connections. Think about a sentence like, the animal didn't cross the street because it was too tired. An old RNN would struggle to know what it refers to, but with self-attention, the model can instantly draw a strong connection between it and animal. It just sees the relationship. Okay, so how does this seeing actually work? How does attention function under the hood? It sounds complicated, maybe a little like magic, but it boils down to a really clever system. It all comes down to three things for every word: a query, a key, and a value. You can think of it like a search engine. For any given word, its query is like it asking, hey, who in this sentence is important to me? Every other word holds up a key, which is like a sign saying, this is what I'm about. The query then looks at all the keys to see which ones are the most relevant. The better the match, the more attention it pays to that word's value, its actual meaning. But they didn't stop there. This is where it gets really cool. They realized, why just ask one question at a time? So they created what's called multi-head attention. They basically run this whole query, key, value process multiple times in parallel. The original paper used 8 of these heads, so one head might be figuring out the grammar, while another might be tracking who's doing what to whom. It's like reading the sentence with 8 different pairs of expert eyes all at once.
Okay, so if you're looking at all the words at the same time, you might be thinking, wait, doesn't word order matter? And you're right, it absolutely does. The dog bit the man is very different from the man bit the dog. They solved this with a really elegant trick called positional encoding. Before anything else, they just add a little bit of math, a unique signal using sine and cosine waves to each word that tells the model where it was in the original sentence. It's like giving each word a GPS coordinate.
So you've got this beautiful, elegant new idea. But in science, ideas are nothing without results, right? And the results they got? Well, this is what blew the doors off the whole field. They weren't just a small improvement, they were a leap.
Just take a look at this table. We're looking at machine translation quality here, measured by something called a BLEU score. All you need to know is that bigger is better. The best models at the time were getting scores around 26.3. The Transformer, the big version, hit 28.4. It didn't just nudge the state of the art forward, it set a whole new standard.
I mean, a jump of over 2 Bluey points might not sound like a lot, but in this world, that is a massive, massive leap. It was a total game changer for the machine translation community. People just didn't see improvements like that, especially not from a brand new architecture. And if that wasn't enough, here's the real kicker. It did all of this while being way, way faster to train. The old models took weeks. The Transformer, just 3.5 days. Why? Because you could throw a ton of GPUs at the problem at the same time, thanks to parallelization. So it was better, and it was cheaper and faster. That's the holy grail.
And really, that efficiency, that's the key to the Transformer's legacy. It's one thing to be more accurate. It's another thing entirely to be more accurate and way more efficient, because that efficiency is what unlocked true massive scale.
So what did that efficiency give us? Scale. The ability to parallelize meant we could stop building models with millions of parameters and start building them with billions, and now even trillions. That's the reason we have the massive, large language models that are changing our world. The Transformer architecture is what made that possible.
When you boil it all down, the Transformer gave AI a new blueprint, a powerful and, most importantly, a scalable way to understand context. It's no exaggeration to say that this architecture is the DNA inside pretty much every major language AI you interact with today. And that leaves us with a pretty cool final thought, right? This whole revolution happened because a few researchers looked at a core assumption that you have to process language in a sequence, and they asked, but do we? What if we just don't? So you have to wonder, what's the next big foundational assumption that's just waiting for someone to challenge it?